presentation of Marcelo Sarandy. Please, Marcelo.
Okay, so just one sec, please. Okay, so thanks, Onofre, for your kind presentation. Thanks the organizing committee for the invitation, and thank you all for coming. Just one second, please. Let me just leave it here. Okay, so now that's fine. Okay, so the aim of my talk is to present some results about many-body localization and its experimental implementation in a quantum annealer. So this is a joint work with Jaime Filho, Zoe Izquierdo, Andrea Saguia, Tamin Albashi, Tai Hen. This is a Brazil-US collaboration, so Jaime and Andrea are from our group here in Brazil, and Zoe, Tamin, and Itai are from the US team. So most of my presentation is contained in this reference here. So if more details are needed about what I'm going to present, please go to this paper, okay? So let me start with many-body localization first. So the concept of localization was first introduced by Anderson, and in Anderson localization, we have non-interacting electrons in a random potential. So in the absence of randomness, the electrons may hop through the sides of the lattice, and we have an extended wave function. Now, if we turn randomness on, and if randomness is strong enough, then the system may get localized and behaving as an insulator, and then we have a probability density that is exponentially decaying, right, around some localization position, like this part. So, but here today we are interested in a different kind of localization, which is many-body localization. So in many-body localization, we have now an interacting quantum system in the presence of a disorder. If a disorder is strong enough, the system may get localized in a general Hilbert space, not necessarily real space, okay? So as a consequence, since the system is localized, we can characterize the MBL phase by the failure of the quantum system to reach thermal equilibrium. So bear in mind that a quantum system in thermal equilibrium is fully characterized by a small number of parameters for an isolated system, for instance, by energy, right? So these parameters are independent of the details of the initial state. So we have two situations in thermal equilibrium. So we have erasure of the memory of the initial state as the evolution time goes to infinity, right? And in the MBL phase, the system retains the memory of its initial condition in local observables if we wait long times. So this is very important for my talk because this is the way we are going to distinguish in the experiment thermal equilibrium from the MBL phase. So in thermal equilibrium, we have erasure of memory. In the MBL phase, we retain the memory because the system fails to reach thermal equilibrium, okay? So this erasure of memory and this thermalization effect can be understood from the eigenstate thermalization hypothesis. So this eigenstate thermalization hypothesis roughly says that individual energy eigenstates, if they live in the same energy window, so they yield the same expectation values for local observables if we wait a long time. So they all behave the same, right? So if we expand the state vector in terms of these eigenstates, and then if we wait long time, suppose A here is a local observable local magnetization, for instance, then we get at the end the expectation value predicted by the microcanonical ensemble, as it is expected for an isolated system, right? So this is the way the ETH, the eigenstate thermalization hypothesis, is a way to explain this apparent paradox of quantum thermalization. That is, that unitary time evolution cannot erase information, right? So if we prepare a system initially in a pure state, and if the system is subjected to unitary time evolution, so at the end, we must have a pure state. We cannot have a mixed state governed by microcanonical ensemble. So the ETH explains how can we get a pure state evolution compatible with microcanonical predictions, right? So the resolution actually is that the memory is not lost in thermalization, but it's hidden by thermalization. This is a mechanism that is similar to what happens in decoherence in quantum mechanics. So here I have an isolated system, and each subsystem of the system serves as an environment to the other subsystems, right? So then, if I prepare a subsystem in some superposition state, as the system starts to interact, the subsystems, right, start to interact with themselves, we have spreading of entanglement, right? We have the information, the superposition that was in the first subsystem, for instance, spreads to the other, we get an entangled state, and so at long times, the information or that initial superposition is inaccessible for local operators. But superposition is still there. We could recover that if we measure global operators, right? But if we are restricted to local operators, memory is apparently lost. But actually, it's hidden, right? Not lost. Okay. So, so this is the approach that we are going to take in this work. We are going to try to investigate if memory is present or not during a quantum annealing experiment. Okay, so our idea then is to implement many-body localization in a quantum computer. Actually, it's a more restricted, noisy version of a quantum computer that's denominated a quantum annealer. Even though I have an optimistic view of the future of quantum computing, we must admit that quantum computers as computing machines are, with current technology, kind of far from delivering their full promises, right? But on the other hand, if we look at quantum computers as simulation machines, machines capable of simulate other quantum systems, then with current technology, we can have a very interesting device that can provide insightful results. So this is what I'm trying to show here. So let me first describe a little bit the model of quantum computing that we are thinking about when we talk about quantum annealers, right? So the first thing is the following. What's the basic element of a quantum computer? Are quantum bits, right? Quantum bits are quantum systems of two states. So for instance, a spin 1/2 is a good candidate for a quantum bit, for a qubit. And then we feed the quantum computers with quantum algorithms that are a set of instructions that operate over these qubits, right? So in the standard model of quantum computing, we have quantum circuits. And quantum circuits are wires and quantum gates. The wires carry the qubits, while the gates implement the algorithms, operates over the qubits. So actually, in most of cases, is the opposite, right? The qubits stand still, and the gates are carried by the wires until the qubits. So, but at the end, the idea is the following. We prepare an initial state, an initial product state of qubits, then we operate over these qubits, and then we measure at the end and get the solution of the problem if your circuit is properly designed, right? So for instance, here, this is the example of the teleportation quantum circuit. So we can do universal quantum computation with the quantum circuits if we are able to do arbitrary 1-qubit gates and an entangling 2-qubit gate. So this is enough for a universal quantum computation with circuit model. And the efficiency of this computation process can be measured in terms of the scaling of the number of gates, which we call the depth of the circuit, right? Okay, this is the standard model of quantum computing. Here, we are interested in an alternative model, which is called adiabatic quantum computing. So, in adiabatic quantum computing, the computation is implemented by a Hamiltonian instead of a circuit. So the Hamiltonian implements a continuous evolution in time. So adiabatic quantum computing is an analog approach instead of a digital approach, right? We don't have discrete set of gates. We have a Hamiltonian that continuously implements the evolution. So we prepare the system in the ground state of the initial Hamiltonian. The Hamiltonian is time dependent. And this initial Hamiltonian is very simple. This ground state is very simple. For instance, it could be the transverse field alone, right? Or any very easy Hamiltonian with a simple ground state. And we encode the solution of the problem in the ground state of the final Hamiltonian, right? There are some strategies to do this encoding. And then if the Hamiltonian evolves in an adiabatic way, so if the evolution is adiabatic, then if I start in the ground state, in the simple ground state of the initial Hamiltonian, I end up in the ground state of the final Hamiltonian that encodes the solution of the problem, right? So the efficiency of the adiabatic quantum computing method is based on the adiabatic theorem of quantum mechanics. So the idea is the adiabatic approximation that says that if we prepare a quantum system in the ground state of a time-dependent Hamiltonian, it will evolve to the corresponding ground state at later times, as long as the evolution is slow enough. And the slow enough here means that the time of evolution must be much greater than the inverse gap squared, okay? So the energy gap plays a very important role in the efficiency of the adiabatic quantum computation method. So we need to understand if the gap shrinks polynomially or exponentially as a function of the input size, right? Okay, so this adiabatic paradigm of quantum computation is especially useful for application in optimization problems, but we can show that if your Hamiltonian is general enough, we can do universal quantum computation with that, okay? Okay, so these universal adiabatic machines are challenging to be built. However, we can have already, at the commercial level, non-universal devices dedicated to optimization problems. These devices, which are noisy versions of adiabatic quantum computation, right, are referred to as quantum annealers. So quantum annealers can be thought as a device that is running in a noisy environment, but that tries to implement adiabatic quantum computation. These quantum annealers are usually not universal at this moment, with current technology at least, okay? So we will use in our experiment the D-wave quantum annealer. So the quantum annealer is this black box here. The dimension of this black box is the dimensions of approximately a human being, right? So this black box ensures that temperatures are close to absolute zero, that we have a shielding from external magnetic effects, that we have high vacuum. So from the engineering point of view, it's a very interesting machine. And from the environmental point of view, it's a very nice also because it consumes just 25 kilowatts of power. So if we compare with larger supercomputers, we can see that this is much less than a supercomputer. Okay, so inside this black box, we have this ARM, and at the bottom of this ARM, we have the quantum processor. And inside the quantum processor, we have the qubits. And in this annealer, the qubits are superconducting qubits, right? Are superconducting circuits that here is represented by these rectangles here. So this is the schematic representation of the superconducting qubits. That is the basic building blocks of the D-wave quantum annealer. And depending on the direction of the persistent current here, we have a magnetic field pointing upwards or downwards. And so this qubit here can be thought as an artificial spin-on half system, right? So the direction of the current defines the magnetic flux, and then we can design an artificial spin-on half system with this qubit. So if we want to go from a single qubit to a multi-qubit processor, these qubits must interact with themselves. So they must be connected. So here in this figure, we have the qubits, which are these rectangles, the circuits, right? These rectangles are the qubits, and these blue balls here are the connectors, the couplers. So in this D-Wave architecture, in this version of the D-Wave architecture, we have a cell composed by 8 qubits, and each qubit interacting with 4 of the others, right? So this is the scheme of the D-Wave architecture. Okay, so then the D-Wave annealer can implement this kind of graph. This is called the chimera graph. This is the older version of the D-Wave annealer. Now they have a new version that can implement a little bit more connected topology. But here, the annealer that we used in our experiment is the D-Wave annealer capable of implementing the chimera graph. So in this chimera graph, I have cells composed by 8 qubits, and in the version that we used, which is the DW2KQ, so it's the D-Wave 2000Q, we have a grid composed by 16 times 16 cells of 8 qubits. So we have about 2000 qubits available, right? Notice that the connectivity is sparse. Inside each cell, each qubit connects with just 4 of the others, right? And they connect vertically or horizontally with the next cell, right? But we can embed a generic graph if we want, if we need, depending on the problem, right? We can embed a generic graph with the cost of any square qubits. So if your totally coupled graph with any vertices must be implemented, maybe you will need the order of any square qubits to implement your general graph on the D-Wave machine. Okay, so let's go now for our results. So what we would like to implement, we would like to implement a disordered transverse field Ising model on a chimera graph. So it's we want to see the Ising system in a transverse field implemented over a chimera graph with chimera graph connections, because this is naturally available in the D-Wave annealer, right? We are using D-Wave here not as a quantum computer, but as a quantum simulator of a physical system. So we are going to implement the disordered model because we want to investigate many-body localization. So we have disordered couplings in the z directions, disordered local fields in the z direction, and the transverse field is not disordered, but this is a limitation of the D-Wave device. So this transverse field is time-dependent, but it's not disordered. So the intensity, the strength of disorder is denoted here as J. So the disorder strength runs in an interval that goes from -J to +J. So we are going to implement different sizes of systems, n equal to 4, 6, 8, and 8 is the limit of the cell in the D-Wave because each cell has 8 spins. But for the theoretical analysis, we will extend the chimera cell for sizes n equal to 10 and n equal to 12, right? So n equal to 10 and n equal to 12 is not directly implementable in the D-Wave because we would have to increase the size of the cell. So 10 and 12 will serve for the theoretical analysis, but for the experimental analysis, we will keep the system up to 8 spins and see what we can see. So the question is there a many-body localized phase for the disordered transverse field Ising model on a chimera graph? So this is the first answer we would like to have. So we addressed this problem first by looking at the entanglement entropy for the transverse field Ising model. So we cut the system in half, right? So we have 4 spins in a subsystem A and 4 spins in a subsystem B, and then we look at the entanglement entropy for one of these subsystems, right? We are looking in the entanglement between A and B by measuring the entanglement entropy. So this is the result we get. So we compute the mean entanglement entropy. So this average in the entanglement entropy is over many realizations of disorder, up to 5,000 for systems up to 8 spins. And we compute this entropy for the eigenstate in the middle of the spectrum. So we diagonalize the Hamiltonian and get the eigenstate in the middle of the spectrum, and then we compute the entanglement entropy. So the results are the following. The mean entanglement entropy is approximately independent of the disorder strength for a small disorder. If J over delta, which is disorder here, the strength of the disorder, if the J over delta is not too large, entanglement entropy is approximately independent of J over delta, right? And strongly decreases for large disorder. So if disorder is large, it strongly decreases. So this reminds us a volume law for small disorder and an area law for strong disorder. Here we have an approximate extensive behavior of the entropy in the low disorder area, and we have an almost constant behavior in the strong disorder area. We cannot state volume law and area law because here we don't have a strictly one-dimensional system, right? We have an almost one-dimensional system, but it's not an exact one-dimensional system. So, for instance, we can't see here the entropy going rigorously to a constant as we would have in a strictly one-dimensional system. But it's similar, right? It reminds us volume law and area law. At least we can clearly see a very different behavior in the average entropy, and it's expected that in a localized phase the entanglement entropy gets very small, and in the thermal phase, the small disorder phase, it's expected that we have an extensive behavior for the entropy, right? So in the localized phase, the system is concentrated in Hilbert space, and then entanglement entropy gets small. So from this plot, we conjecture that we have a localization transition in this model. And how can we characterize the critical point? We use the standard method of looking for the variance of entanglement entropy. So this is here in the inset. We computed the variance of the entanglement entropy after many realizations of disorder. And the idea is that close to the critical point, the system is kind of undecided, right? If it behaves like area law or like a volume law. So the variance is large, close to the critical point. So the idea is that the critical point of the MBL transition can be characterized by looking at the maximum at the variance of entanglement entropy. So we just look at the maximum for up to 12 sites, and we can see this behavior of maximum, right? And we just took here the value for the n equal to 8 spins, because this is the size of a single cell in the D-wave experiment. And this precursor of the critical point, J over delta critical, is around 4.8, right? So around 4.8 is the precursor of the critical point for 8 spins. Of course, that if we want to characterize a criticality, we should go to larger sizes and try to see by a finite size scaling, the true critical point. But we don't want to do this here because we want to check what the results are in the experiment. And if we do the experiment with 8 spins, it's expected that we get some results similar to this 4.8. This is what we expect. So now, this is one way to characterize, but we can provide further evidences of this this transition, right? So first, we can explore the other eigenstates, not only the eigenstate in the middle of the spectrum, but we can look at all the others, right? And this is what is called the mobility edge. So we define a dimensionless energy density here, and we plot the maximum of the variance as in the inset of the plot in the last slide. But now for all the states, all the spectrum, right? For 8 spins. So what we can see here is the ground state. So the ground state is the density 1 here, due to our definition of the density. And here in 0 is the most excited state. Here in the middle is the middle of the spectrum, right? So see that the middle of the spectrum is indeed the eigenstates that are hardest to localize, right? So the eigenstates in the middle of the spectrum are the eigenstates that are the hardest to localize. They are the eigenstate with the larger maximum variance of entanglement entropy, right? So this is why we usually look at the middle of the spectrum, because if we get localization in the middle of the spectrum, we get localization for the other eigenstates. Remember that, bear in mind that the MMBL phase transition is a dynamical phase transition. We can see this transition in individual behavior of eigenstates, right? So if we look at the middle of the spectrum, we have the eigenstates which are the hardest to localize. Okay. So as a further evidence for the localization transition in this model, we consider the spectrum statistics of the energy, right, for finite size samples. So the idea here, this characterization is works in the following way. So for each disorder realization, we consider the energy level spacing, the gaps, right, delta n, that's equal to En plus 1 minus En, right? And these En are the energies, and we list these energies in ascending order. So we list the energies in ascending order, and we compute the gaps, all the gaps, right? And then we compute the ratio of adjacent energy gaps. This is Rn. So we just take the minimum of the gaps, the neighboring gaps, over the maximum of the neighboring gaps. And then we average Rn over all energy gaps and over all disorder samples. This yield this identifier that we call the average R, right? It's average R, so is this gap ratio averaged over all the energy gaps and over all disordered samples. So what we know is that for the thermal phase, from results coming from random matrix theory, we get that for the thermal phase, when disorder is small, this average R should be governed by a Gaussian orthogonal distribution. And this average R is this value here, right? This is not from our results. This comes from other references. But this average R is 4 minus 2 times the square root of 3. So we plotted here this dashed line, right? Denoting this limiting value for the thermal phase when we look at the ratio. And then for the localized phase, since the eigenstates are uncorrelated in the localized phase, they should obey a Poisson distribution. And this average ratio is 2 times logarithm of 2 minus 1. And I put here this dashed limit here. And then when we plot this for our results, we can see that as we increase the size of the system up to n equal to 12, for a small disorder, we can see the system converging for this thermal phase, right? This Gaussian orthogonal distribution. And when the disorder is strong, very strong, we can see the system converging to the Poisson distribution limit here. So this is another evidence that we have a localization transition in the transverse field Ising model defined over a chimera graph. Okay. From this method, I can't compute the critical point, at least not in a trustable way, but we can compute the critical point by using the variance as I showed before. Okay. So now, finally, let's go to the experiment. Let's see what we learned from the experiment. So in the annealer, we have a time-dependent Hamiltonian. So it's not a time-independent as we want. We'll have a time-dependent Hamiltonian. And this Hamiltonian interpolates between the transverse field, it's HTF, until the classical Ising Hamiltonian, right? This HI here. So our aim is to simulate the dynamical of a time-independent disordered transverse field Ising model. But the quantum annealer deals with a time-dependent Hamiltonian. So how can we manage that? So the idea is the following. We use two ingredients in the quantum annealer. We use reversal annealing plus pulse. And this is what we do. In the quantum annealer, we have a schedule for these time-dependent parameters, A of S and B of S. Notice that A of S starts as 1 here, right? And decreases until 0, right? And B of S is the opposite, right? So we have this S as a as a dimensionless time parameter, this S, right? It's a dimensionless time. And the schedule of time variation is provided as in this plot here. So we are turning on B and turning off A of S. So what we do is that we use reversal annealing. We start from S equal to 1, not S equal to 0. We start from S equal to 1 because we want to start with the classical disordered Ising model, HI. So we need to start from S equal to 1. Then we decrease the time until an intermediary S time, which we call SP here. And then we pause the system. So in this plot, we can see this, right? We decrease S until some time, and until S achieves an intermediary S star or SP time, and then we pause the evolution of the system during some time. And here in this pause is that where we can see the time-independent transverse field Ising model. And then at the end, we put S to go back to 1 again, and we measure the state of the system at the end, right? So we can implement a time-independent transverse field Ising model by using this pause here. Okay, so bear in mind that this ratio B over A for a time SP sets the disorder strength, right? Because this A multiplies the transverse field and B multiply the Ising Hamiltonian. So they defines the strength, this energy scale of the Hamiltonian. So the ratio between B and A sets the disorder strength of the problem. So I control the disorder strength by just defining a convenient SP. So if I want some amount of disorder, I just let the system go from S until the convenient SP that implements that amount of disorder, okay? So the results, the experimental results are the following. First, we consider single cells, and then we use 48 different cells. And on each of these cells, we run 200 instances, right, of disorder, 200 realizations. And each run consists of 1,000 anneals, right, annealing process. And then we average all of these at the end. So reversal annealing and the forward part of the annealing at the end are performed at the rate of 1 anneal per microsecond, right? And the pause duration is 100 microseconds, okay? So we pause during a long time compared to the first and the last part of the annealing process. Okay, and these are the results. So here I'm showing the local magnetization. So each point here is the mean magnetization at a specific disorder, which is defined by the ratio B over A, right? So B over A can be thought here as the disorder strength. So we can see here that if the disorder is small, I have zero magnetization. And the initial states here is all the spins up or all the spins down. So if I evolve at the end, this is when I measure magnetization at the end of the process. If the magnetization is zero, it's because I'm losing information. I'm losing memory here, right? Memory is hidden here. But then if disorder gets strong enough at the end, we can see the memory coming back, right? So here for the very strong disorder, I can see magnetization equal to 8 again. And here I'm dealing with 8 spins. So this is all the spins up. And this plot here in the low part is the all spin down. Okay, so we can see here the onset of non-vanishing magnetization occurring at the ratio, the disorder strength of 3.57, right? So this is lower than the 4.8 critical point that I showed before, but this is fine. It agrees with the mobility edge because we are not here necessarily in the hardest state to localize, right? So the expected result here is to obtain a disorder critical point that it's smaller than the 4.8 that I have shown before, because we are not here in a single eigenstate in the middle of the spectrum, right? Here the system is under decoherence and we are not exactly in the middle of the spectrum, so it's expected that we have a close result but smaller, right? Okay, so let me go a little bit faster here. We also checked what happened for double cells, double cell instances. So instead of considering a single cell, I consider here 2 cells, right? And then we use 35 a pair of cells to implement this realization. Here we use less cells that are available in the system because we avoid using the edges and we leave one unused cell between used cells. So we can't use all the cells of the systems. The average works better if we use less cells, not using neighboring cells to compute averages, okay? So for double cells, the result is practically the same. We can see the onset of vanishing magnetization in some value that is compatible with the theoretical prediction of the onset of memory, right, in the system. So we also verified if the MBL transition could emerge, or some falsification of the MBL transition, right, could emerge from other causes that are not disordered. So we considered the uniform case. So let's take the transverse field Ising model in the uniform case. So if we consider the uniform case, of course, it's not expected to have an MBL phase transition because we don't have disorder. But in any case, what we get here is that the onset of memory does not appear for the uniform case in the same point, 3.57, right? We can see that here that for the disordered case, the onset of memory occurs here in the 3.57 critical disorder. Now, for the uniform case, the memory will appear just in the limit of very, very, very strong disorder. And this does not mean an MBL phase transition, right? We don't have an MBL phase for the uniform system, but this comes because in this limit of disorder, SP is very, very close to 1. So the transverse field is too weak. And then the system is practically kept in the initial state from the beginning, right? So the system is frozen. So the behavior is very different. If I have a disordered system and a uniform system, the experiment runs completely different, okay? So this is a point in favor of our results. Finally, we also looked at the classical simulation of the annealing process, because our result suggests that we are experimentally observing the theoretically predicted localization transition. However, as I'm going to see now, I'm going to show now in this slide, at this stage, we can only say that we have compatibility with the expected behavior of a many-body quantum system. This is because we can qualitatively reproduce our results by using a classical simulation method, which is denominated the spin vector Monte Carlo approach. So by using SVMC, we can qualitatively reproduce the experimental results. So in the SVMC, the qubits in the Hamiltonian are replaced by rotors, by 2D rotors. I replace sigma z for cosine of theta and the sigma x by sine of theta, and then I have a classical potential and 2D rotors. And then I implement Monte Carlo practically as usual, right, Metropolis. And if we do that, what we get is a behavior that is similar to our quantum experiment. So I can see here the onset of memory in the order of 10 for the disorder, right? So not 10, a little bit less. So it's close to the critical point that we found before. And for the uniform system, I can see for very, very strong disorder the onset of memory. So the conclusion is that our experiments are compatible with the localization transition and are at least a simulation of the localization transition, but they do not mean a proof of concept of quantumness at the D-Wave device, right? I cannot use my experiment to say, oh, see, we have MBL in the D-Wave, so D-Wave is a device that works in a quantum way, right? Because here I'm using a classical method that reproduces the result coming from the D-Wave device, right? But for us, this is not a problem, because we are not interested in proving here that the D-Wave device is quantum. We want to use the D-Wave device to simulate a phase transition in a disordered system, right? We want to use D-Wave as a simulator. So for us, this is not a problem, but this is an alert that we cannot take this result to use as a proof of concept of quantumness for the D-Wave device, right? So to finish my conclusions, first of all, we have used the D-Wave device as a programmable device, because we can individually program the couplings, the local fields, to study critical properties of quantum systems. So we are using a quantum computer as a simulation device, right? And to my knowledge, this is the first time that the critical point of the D-Wave quantum annealer is characterized when we are interested in this MBL phase transition. Of course, we did not consider in the theoretical analysis the effects of the coherence, and they are important. And this is a point that we want to explore in the future. So the second point I'd like to emphasize is that the current hardness of adopting a quantum annealer as an optimizer, that means as a quantum computer, does not prevent its current applicability as a simulator, right? So the quantum annealer can be a very interesting simulator of disordered systems, even though as a quantum computer, the quantum annealer is not close to deliver its promises, right? So as a third point, we'd like to look more carefully in these witnesses of genuine quantum behavior, because we look at the magnetization here, and as I showed, magnetization can be reproduced by a classical simulation method, the classical Monte Carlo method. So we are interested in finding witnesses of genuine quantum behavior that can be measured in the D-Wave device, and that cannot be reproduced by a classical method, right? So this is another point of interest for future investigations. And finally, I think that an interesting further development would be to look at quantum thermalization in a scenario of open quantum systems. This means in a scenario where we have decoherence, because we know that the D-wave quantum annealer is full of decoherence, right? Decoherence is there even though we have that black box that tries to avoid at most the interaction with the environment. We know that decoherence is there. So it's an interesting device to understand and to model decoherence and their effects on the quantum thermalization and many-body localization transition, right? So basically, that's it. And thanks for your attention, everybody.
Please, people who have some questions, raise your hand, please. Remotely. There are some people. Here we have Marcelo, please.
Okay.
Hi, Marcelo. Thank you very much for your contribution. It was very nice. And I have more a curiosity. You commented that the level space in statistics is different in the MBL and the thermal phases. Do you know if the own wave function statistics, the distribution of intensities of the wave function, if this distribution is different in these two phases?
The distribution of the wave functions, you mean?
Yeah, the wave function distribution, so the intensities of the wave function, this is different in these two phases, or not have?
I'm not sure, but I'm not sure about the wave function distributions. But the idea here is that in the localized phase, we don't have this eigenstate thermalization hypothesis, of course. So then we don't have these eigenstates behaving similarly, right? They are uncorrelated. And since they are uncorrelated, we have a Poisson distribution describing the system. But I'm not sure if this is reflected in the wave function distribution. I think maybe it's possible, right?
Without interaction in the Anderson localization problem itself, in the extended phase, it's low disorder, and the waving function is structureless. It's like a white noise, structureless. And in the localized phase, it has an exponential distribution.
Yes,
I think similar picture for this NBL problem.
Yeah, I think that this is a good quantity to look at. I don't have the answer, but I think that it's a quantity that for sure it's interesting to look at the wave function distribution, right?
Okay, thank you very much.
Thank you. Nice to meet you.
Nice to meet you. Some additional questions? Okay, here we have Rodrigo. Please.
Oh, hi. Thanks for the interesting talk. You focused on this chimera graph, but I was wondering if it's possible to switch off some couplings in the D-wave computer so you'd have something closer to the usual transverse fields Ising chain, just like nearest neighbors. And then in that case, perhaps you might look at the dependence on system size, or is there really some advantage in looking at the chimera graph as compared to the chain?
Yes, this is a good point. Yes, it's perfectly possible to implement any graph. You can implement a chain. You can implement a square lattice. You can implement anything. But then you can embed in the chimera graph your topology, right? Your connection, and this has a cost, and the cost is at most n squared. So if you want to implement a chain with n spins, you will probably need n squared spins to implement in the chimera connections, right? So, but it's possible. It's perfectly possible. There is a technique called the minor embedding. In this minor embedding, you can implement anything, but by using additional spins to your original system.
Okay, thanks.
Okay, thank you.
Any more questions? Okay, Marcelo, just I have just curiosity also. What about the? Do you know how it's possible to simulate like real quantum computer, like IBM computer?
Sorry, it's possible to simulate what?
IBM computer.
What kind of computer? Sorry.
IBM, there's a available by internet IBM quantum computer. You know, I hope you know.
You mean if it's possible to implement everything in cloud computing?
Yes, and compare your vessels or what.
Yes, sure, yes. All these systems are available by using cloud computing if you want, right? So the computer that we used the D-Wave annealer that's housed at NASA because one of our collaborators works for NASA. But you can have access to these quantum computers here in Brazil using any cloud computing service. For instance, Amazon offers these services, right?
Okay, thank you. Thank you once more.
Thanks a lot.
Thank you, Marcelo. Okay, our next presentation is in 20 minutes. Yeah?
20 minutes.
Yes, okay. 20 minutes. Yes. Yes, we got